Thanks for tuning in today. What we're going to talk about now is the camera and the RGB color model. So, what's the difference between your digital uh, camera and a dedicated astronomy camera? So that and the key points about a CCD astro camera. Really, the primary advantage is really sensitivity, because the types of things we're trying to record in deep space is are very faint. Typically you can't see them with the human eye unless you're in a very dark area with no light pollution, somewhere out in the desert or in the mountains. So the more sensitive the camera, the shorter exposures required to detect faint detail in these deep space objects. And CCD cameras really are up to 50 times more sensitive than a standard digital DLSR. And they're best for urban light polluted areas, and most of us live in those types of areas. They have greater dynamic range. In the end, it's easier to use it. It may seem more complex because if you're just, for example, just using a dedicated monochrome, you're going to have to create color by taking 3 different channels, RGB. But in the end, it's just better. Believe me, this is through personal experience. Now, the digital DSR, your mirrorless camera, obviously it's optimized for the visual spectrum here on Earth. But the challenge with it is you typically have to do very long exposures, and that creates problems for a digital DLSR where you're having to take, for example, in a night, maybe 200 frames and very long exposures. The sensor tends to overheat. It blocks hydrogen alpha wavelength, and that's something that you really want to be able to record in deep sky. There's ways around it, but it just makes it just very difficult to use it for deep sky. And it's okay for lunar and planetary, but it's just not ideal as a standard astronomy camera. And you'll need more pre and post processing for doing things like deep space objects. The difference between color and a monochrome sensor, so there are the same thing in your digital DLSR and the same thing with astronomy cameras. You can get a one-shot color astronomy camera, or you can get a monochrome. And so here's the difference. The difference is a color camera has what is called a Bayer matrix on top of it. So essentially it's an array or it's a matrix of red, green, and blue, which actually makes up a color pixel that enables the camera to render scenes in color. Now, there are monochrome sensors out there. The matrix is on top of a monochrome sensor. There are cameras that are just monochrome only. There's a huge advantage. As I talked about earlier, it's sensitivity. And basically, you don't have this matrix on top of it, so you're essentially getting higher resolution, more pixels recording the light, and a hell of a lot more sensitive. So it really is ideal if you really want to be serious about astrophotography, especially deep space astrophotography. It's just a better way to go. It might seem more complex, but in the end, it's actually simpler. So in the observatory, in the examples we'll be using in the subsequent videos, we have 3 types. We don't use DLSR anymore for various reasons. It's just not optimal for astronomy in general. It's okay for lunar and planetary using video. We'll talk about that in later episodes. But essentially we have 3. We have a camera that's for planetary and solar and lunar. It's used in video mode. Then we have our deep space cameras. One is a monochrome, one's a color. And the next is a one for auto guiding. So now what we're going to do is just go into a quick video, and we'll see the cameras live, in the observatory. So we're going to just do a very brief video here of the different cameras we use for astrophotography in the observatory. The first one is it's a Starlight Express. It's a Trius line. This is actually the a one-shot color. We also have an exact same, configuration for monochrome, which is super sensitive. The beauty of these cameras are they stay extremely cool, so you can do really, really, really long exposures. If you take a look at this thing is built like a tank. It's got a fan inside the body, it's got an external fan, and it's got these cooler fins so that you can do, you could do exposures 10, even 20 minutes if you want. Typically we do like 5-minute exposures. So this is, a CCD camera. Basically what you do is you just screw this onto the back of the telescope. What we have here is a Explorer Scientific 80. It has a field flattener. This is for preventing vignetting and keeping a very flat field. And then you screw the camera on the back. That's kind of like how it's configured. We'll go into the telescopes later in a different video. But these cameras are just amazing. Now you don't have to buy, this is a little bit of an expensive camera, but there are other cameras that will do the equivalent that are less costly. For example, we'll talk about the Zwo camera line next, but these cameras are just amazing. They're fantastic. The unfortunate part for Starlight Express, they don't do a lot of marketing about their cameras, but they are just excellent cameras. You can record the most finest detail in the deep space objects, and that's what we're going to be talking about in these tutorials. All right, next this is made by Zwo. This camera is actually, it's got video capabilities, so this camera is used for planetary, solar, and lunar imaging. So it seems kind of strange that you say, oh, well, we're using a video camera for these types of objects, but that's the best way to handle those types of objects, because the objects are so small relative to deep space objects that you have atmospheric issues. So what you do is you take 2,000 or 3,000 frames of video, and we have special software that goes through, and then what it does is it selects the best and sharpest images and it stacks them into a final image. Same thing here. This is actually this is a monochrome camera. Same thing. It's got a USB 3 port. It's not cooled, but it doesn't have to be because you're only doing short videos, and it attaches to this telescope similar way. It just threads right in. And it's a really nice little camera. One thing to mention is that these cameras, they're not that high resolution, as compared to your standard DSLR or your mirrorless. But what you want is sensitivity. So these cameras are designed to be very, very, very sensitive, and that's what we want. And then what we do is we stack these images. Sometimes, in the case of the planetary, it's thousands of frames. In the case of the deep sky imaging camera, that's could be anywhere from 200 to 300 frames. And what you're doing is you're dithering and you're pixel shifting. So you're actually taking all of those images very much like you do in your some of the more advanced mirrorless cameras today, where they do high resolution mode, where they're actually slightly shifting the image, pixel shifting. We're doing the same thing in astrophotography, really, and we're getting stunning images, beautiful, sharp images after we post-process everything. So you don't need big sensor, high resolution. What you need is sensitivity. Now the last camera I'm going to talk about is a guide camera. You need the guide camera for auto guiding, so you can track stars as the object moves at night. This gives very, very fine-grained tracking, so you can do really long exposures. Essentially what you do is you take the guide camera goes into this guide scope, goes in the back here, and typically you mount it on top of your main astronomy camera. Like below here is the Explorer Scientific 80, which is it's a triplet APO, and it's a very nice scope. So that's kind of like your basic setup. Those are your basic cameras. We used to use a DLSR. Don't use that anymore. You can put your DLSR on the back. This is a T-thread. All you need is a T-thread adapter, but we don't recommend really using a DLSR. I mean, it's okay for lunar and planetary, but as we discussed in the presentation, it's just not optimal for astrophotography. Okay, so let's go back and finish up the presentation. So now we're going to get into some processing. But first, let's just talk about the RGB model very quickly. So there's the way you get color using, for example, a monochrome camera is you're taking 3 separate channels or 3 separate series of exposures stacked into a red, green, or blue channel. And so you can use actual red, green, and blue filters, or you could use different types of filters to get a color effect. So the first and most simplest way, we usually use this for galaxies, is we take a red, green, and blue filter. And for example, in this example, these images were taken with a Trias 814 monochrome camera. There's been a lot of processing before that, but we're going to keep it simple. We're going to start with the results and then work backwards into the complex workflow of doing this. It's not so complex, but we start simple and then we incrementally add different steps so it's easier to understand the process. And then we combine those, we stack those, we align them and stack them, and we create a color image. So this was taken on the left-hand side are the individual red, green, and blue channels, and then we combine them into a full color. And this is Pickering's triangle. It's found in the Cygnus loop. The other very popular, at least made popular by Hubble, is called the Hubble palette. And the way it works is that you take narrow band filters and then you make recordings of the sulfur emissions, oxygen emissions, and hydrogen emissions in deep space objects, typically nebula. We don't typically do this for galaxies. We do these for nebula. So this is the Cave Nebula. It was taken through narrow band filters. And the beautiful thing about this, number one, it's not only does it render better, but many of us live in light polluted areas, light polluted skies. And so you want to be able to penetrate all of those aberrations caused by light pollution, and mostly it's light pollution. And that way you isolate the only thing you're interested in. You're only interested in the very narrow wavelengths of the emission nebula. And so in this case, we used a sulfur, hydrogen, and oxygen narrowband filter. And in the Hubble palette approach, we assign sulfur to red, hydrogen to green, and oxygen to blue. And then we end up with this very stunning looking, beautiful nebula. So what we're going to do now is we're just going to go into and just show you examples in Photoshop of how this is done and how the RGB. Okay, here we are in Photoshop. And I think it's best to kind of show these RGB principles, just using live examples. So here we are in Photoshop. This is just a normal, digital image taken with, with a typical 24 megapixel, digital color DLSR. Now, if you go into Photoshop and if you go over here to this tab, when you open it up, you'll see this little box here. And typically, a lot of us will be familiar with the background. But if you click over here, you'll see channels. And there's a red, there's a green, and the blue channel. And these are the composite monochrome channels that make up this color image. So it's the same thing we've been talking about previously in the presentation about how we do it in astronomy. It just so happens that with a modern, digital DLSR or mirrorless camera, everything's done for you in one shot. So Let's go on to another interesting example. This actually is an example. Um, don't worry, these are dried flowers, and this was just an experiment. But it was taken with a Leica monochrome camera. So Leica is a camera manufacturer. You may be familiar with them. They make rangefinders and various other types of cameras. But this was taken with a monochrome rangefinder camera. It's called a Leica Monochrome 246. And it was taken on a tripod, same image, but through three different filters. I used red, green, and blue astronomy filters. And so I took, there's a photograph of the red, there's the green and the blue, and then stacked them in Photoshop and came up with this color image. It's kind of an interesting image. Kind of reminds me of the early color photography. I guess it's in the 20th century. It kind of reminds me of autochromes. It's kind of an interesting look, but it just goes to show you that you can get. That's how we operate on the astronomy side, is we take separate channels of red, green, and blue, and then we stack them to make a color image. Now here's another really interesting one. This was taken with the camera that you saw previously. It's the Zuo ASI 174. It's a monochrome camera. Same thing. This was taken actually in video mode. So the reason why we use video is that there's a lot of atmospheric disturbance when you actually look at an object like the moon or the sun or a planet. And you'll notice that sometimes it's in focus, sometimes it's not. So what we do is we take, a couple thousand frames of the object. We have special software that goes through and picks out the best frames so that you get a really clear image. And then you stack that image, which is even better. And so this was done with red, green, and blue filters. Now, yeah, and the moon does have color. And just to give you an idea, the shades, the blue and orange shades indicate volcanic lava flows. There's the dark blue areas, indicate that this area is richer in titanium-bearing materials. The pink colors indicate regions of iron poor but aluminum rich, and the blue ways indicate titanium, like I said before, titanium rich. And then there's orange and purple, which indicate lack of titanium and iron. So it's kind of interesting. And then, of course, if we go to the, I did a color enhancement to kind of just show those principles and all the different elements and metals that you find on the moon. Sort of interesting. Again, if you go and take a look, these are the actual individual video frames stacked, a couple thousand each. So you're looking at probably, I don't know, something like maybe 4,000 to 6,000 frames in total to make up this image, and it looks quite good. It's better than what you would get with your 64 megapixel Sony A9, for example. And this is just color enhanced, so just to give a better illustration of the elements you find on the moon. So next, we're going to go into, we're just going to construct a color image, and we're going to use the individual sulfur, hydrogen, and oxygen frames that we built using our software. Now, each one of these individual frames are a result of. We're going to get into the processing, a little complex, not really, but we stacked about 40 to 50 frames of individual long exposure photographs of 3 minutes each. Then we stack them, we process them. There's a lot of things that we do to get to this point, but we're going to keep it really simple. I'm just going to show you how we construct an image. And so what I usually do is, once I have my RGB frames, and in this case, we're using the Hubble palette, which assigns sulfur to red, hydrogen to green, and oxygen to blue. What I typically do is I'll just take one frame and I'll just copy it. And then I'll go up and I will create a new document. And Photoshop is smart enough to know that you want to keep it same size as the image you just have in the clipboard, and you say yeah. And you go over here and you'll see what all the different attributes that you want to assign to this. But make sure that you click here and you say RGB color. And well, I guess we're using we're using JPEG, so I'll keep it at 8-bit. But typically I do this I'm doing this only for illustration purposes. Typically I do TIFF. If I have a TIFF image, I always select 16-bit. But we're going to keep it as 8-bit, keep it simple. And so we'll say create. Okay, so we go back over here. We see there's our layers. There's the background. It's blank. But I go into my channels, and I'm going to go ahead and assign that. What I did is I copied the sulfur frame, and I'm going to just paste it into the red. So paste, and there's my red. And you can see up here, there's your red channel. Now I'm going to go into green. So to get to green, it's hydrogen. So I'm going to go back to my hydrogen frame, do a cut and paste. I'm going to cut, go back to my document, paste that into the green channel, and there we have kind of the two colors starting to build up. And then my last will be my blue, and that's my oxygen frame. Take my oxygen frame, Control C, and paste that into the blue, and voila, there is our color image. So that's kind of the basics. It's good to understand the basics of all of this, because as we go into the videos and add complexity, you'll have a better idea of what's going on. Okay, so now that you've seen how all of this works, if you're interested, you might want to try a very simple example. So the assignment for this week is, combine the monochrome files into an RGB color. And just like we did, you can use the Hubble palette, but it's kind of interesting. Try different RGB combinations, like, assign hydrogen to red and oxygen to, green, sulfur to blue. And you'll get various different combinations of colors, and hey, see which one you like. All the files are there at this link. So if the links this link is below in the show notes. It's a zip file, so when you get to the page, make sure you just click on the link for video 2. It's a zip file, and it has the presentation that we've used today. It has all of the monochrome files as well as the color file, so that you can use and go ahead and process those yourself. And so make sure that just make sure that it's a zip file, and you're going to have to unpack it. Once you download it, you should be able to just open it right up. So thanks for watching. And if you've liked this video, please comment, like, share. Would love to hear if you have any comments. Was the video too long? Is it too simple, etc., and whatever. But again, thanks for watching, and tune in next week for our next video on astrophotography for photographers. Thanks for watching.